So let's solve this question. We have been given 4 processes and we have to find the various parameters that are associated with these processes, and using which scheduling algorithm? Using the round robin scheduling algorithm. Now, the round robin scheduling algorithm works on 2 different fronts. One is the criteria and the other is the mode. Mind you, the criteria for round robin algorithm is the time quantum and the arrival time, and the mode is preemptive. So what do I mean by a preemptive mode algorithm? A preemptive mode scheduling algorithm will involve processes which will give up the CPU midway their execution. So I'll just take up this example, I'll solve it, I'll discuss all the parameters that can possibly be found with this, and I think everything will be clear by then. So now, in order to solve such questions, what you should do is you should take help of the NAT chart. So let's just derive the NAT chart first. Mind you, the time quantum is given by delta, and it's 3 in this case, 3 units. So my time quantum that is given is 3 units. Now, in round robin scheduling, we also have to maintain a queue data structure. Okay, so this is my NAT chart and this is the queue data structure that I'll be maintaining. This is my queue. Why do I need the queue and how it will be used? I'll explain along the way as I solve this question. Now see, we have 4 processes. What is AT? AT is the arrival time and BT is the burst time. Burst time or service time or execution time. Now we can see that 4 processes are present. Out of these 4 processes, P1 and P2 arrived at time unit 1. P3 arrived at time unit 3 and P4 arrived at time unit 16. Remember that these times that are given here are all relative time. That means it's not that P1 arrived at, 1 p.m. or 1 a.m. Nothing like that. It's just that P1 arrived at time unit 1 relative to P2, P3 and P4. And the same for other processes. And the times that we consider for solving such process scheduling problems always begins from 0. So the CPU will start waiting from time 0. Now at time 0, since no process is available, the CPU will remain idle. So the CPU will remain idle for 1 unit. Because see, during this 1 unit of time, no process is available. Now, we find P1 and P2 to be available at time unit 1. How does round robin scheduling work? In round robin scheduling, first the processes are brought into the queue and then they are given control of the CPU. So that's how it works. First the processes have to come into the queue based on their arrival time. So whichever process has a lower value for arrival time will get into the queue first, and as a result will get hold of the CPU first as well. So here we can see that P1 and P2 both have arrival time as 1. So now both will enter the queue. Now which one will enter first? If the arrival time happens to be the same for 2 processes, then the process number will act as a tiebreaker. So since P1 has a lower process number, it will enter the queue first. So P1 enters the queue followed by P2. Now after these 2 processes have entered the queue, they will be given control of the CPU. That means they will find a place in this NAT chart. So how will it happen? P1 will be taken out from the queue and given control of the CPU. So it will make its way to the NAT chart. For how many units? For time quantum units or for time quantum time. Or it may so happen that the time quantum is greater than the burst time. Then the process will execute for burst time units. We'll see that scenario as well. For now, let's see that, okay, one mistake here, sorry, this will be P1. So now we can see that P1 has got hold of the CPU. So its burst time is 4, the time quantum is 3. We take the minimum of these 2 values. So we'll execute P1 for 3 units. That means till 4. So P1 has executed till the 4th unit of time. Now, the interesting thing is, in this interval of 1 to 4, we can see that P3 made its way into the queue. So now P3 is present in our queue. So P3 is present. Now, as we find P3 to be present in the queue and P2 also there, but P2 is before P3, so P2 will be given the CPU next. Now, what about P1? P1, mind you, has not finished its execution completely. It has run for 3 units of time, so it still has 1 unit of burst time or 1 unit of service time left. So it has to be brought into the queue again. Right? Now, P2 will be given control of the CPU. Now, as you can see that P2 has a burst time of 2 units and the time quantum is 3 units. So, if the burst time happens to be less than the time quantum, then we'll run the process for the burst time unit. We'll always go for the minimum value. Out of these two, which is the minimum value? 2 is the minimum value. So P2 will run for 2 units and it will complete its execution. So since P2 has completed its execution, it need not be brought into the queue again. Fine. Now in this interval of 4 to 6, has any process arrived? No. Only one process is remaining, that is P4, but its arrival time is 16th time unit. So it is yet to make its way into the system. So now we have P3. So P3 will be given control of the CPU. For how long? For 3 units, because out of 3 and 4, 3 is minimum. So it is allocated 3 units of time. And since it has 1 unit of time still left for execution, it will be enqueued once again. And now whose turn is it? It's P1's turn. So P1 will be allocated CPU for 1 unit. I hope it's clear by now why 1 unit and not 3 units, because out of these two, 1 is the lesser value. So now P1 has completed its execution, so we need not push it back, we need not enqueue it again. But in this interval, we find that no other new process has arrived, only P3 is available. So P3 gets hold of the CPU, and for how long will it run? It will run for 1 unit. Now see, this is interesting. After P3 completes its execution, there is no process available with the CPU. That means till the 16th unit of time, the CPU will remain idle. So for 5 more units, that means till the 16th unit of time, the CPU will remain idle. The CPU has nothing to do. Precious computation time is wasted. Now, at this 16th unit of time, P4 will make its way into the system and as a result into the ready queue. After it makes its way into the ready queue, P4 will be scheduled. Now see, P4 will run for 2 time quantum units. So first P4 comes in, runs for 3 units, and then it is again pushed into the queue, and then again it is allocated the CPU for 3 more units because its total burst time was 6. So it runs for 22. You could have shown it together as well. That means I could have written I could have allotted just one slot to P4 starting from 16 until 22. Anyway, even this is correct. So this is my NAT chart. So what does the NAT chart display? The NAT chart displays the order of execution of my processes and also the time at which they're giving up the CPU and again getting it back, and possibly the time at which they have completed their execution. Now, after this, what we have to do is we have to find a few parameters that are commonly associated with these processes. The first parameter of interest is CT. What is CT? CT is the completion time. Completion time refers to the time instant at which a process has completed its execution. Now see, as I mentioned right at the beginning, that round robin scheduling is a preemptive scheduling algorithm. It's a preemptive CPU scheduling algorithm. That means while the process is still running, if it exhausts its time quantum, then it will have to give up the CPU, or the CPU will forcefully be taken away from it and given to some other process. Now, in order to find the completion time of such preemptive scheduling algorithms, what you should do is you should look at the NAT chart from right to left, not from left to right, but from right to left, and the first end time that you find for a slot will be the completion time of that process. Let's see. See, I am scanning the NAT chart from right to left. So while scanning the NAT chart from right to left, I find the slot for P4. And the end time of that slot is 22. That means the completion time of P4 is 22. I hope you're getting this. Now I'm scanning, going to the left. Yes, I have found a new slot. See, here also I found another slot. I had found another slot, but the slot was for P4 itself, and I've already found the completion time for P4, so I'll ignore this. Now, while scanning, the next unique or the next new time slot that I have found is that of P3. And where does that slot end? That slot ends at time unit 11. That means the completion time of P3 is 11. Now see, again I find a new slot. That new slot ends at time unit 10, and this is the time, and this is the slot for P1. So P1's completion time is 10. And again I encounter a slot for P3, but I've already found the completion time for P3, so I will ignore this. Now P2, this is a new slot that I've encountered, and its completion time is 6. So the completion time of P2 is 6. I hope this is clear. Next parameter that we have to find is TAT, the turnaround time. What is the turnaround time? The turnaround time, mind you, is the difference between the time at which the process entered the system and the time at which it left the system. So turnaround time gives us the time interval for which the process was present in the system, right? So it gives us the time units or the time interval for which the process executed in the system. So the formula for turnaround time would be completion time minus arrival time. So if I find the turnaround time, what will it be? 10 minus 1 is 9, 6 minus 1 is 5, 11 minus 3 is 8, and 22 minus 16 is 6. Another popularly asked for parameter is waiting time. WT stands for waiting time. Now what is waiting time? Waiting time is the time spent by a process waiting for the CPU. Waiting time is the time spent by a process waiting for the CPU. Now see, how do we find the waiting time? See, turnaround time, what did I say? It was the total time spent by a process in the system. And out of this total time, what is the burst time? Burst time is the useful time, the time for which this process actually worked using the CPU. And what about the remaining time? That means from turnaround time, if you take away the burst time, you're left with the remaining time. And what is this remaining time? This remaining time is the waiting time, right? Because the process had nothing to do and was waiting for the CPU. So in order to find the waiting time, we will take the turnaround time and from it subtract the burst time. So 9 minus 4 will give me 5. 5 minus 2 will give me 3. 8 minus 4 will give me 4. And 6 minus 6 will give me 0. So what does this mean? This means, okay, did I make any mistake? Turnaround time minus burst time. No, I think we are good to go. Yeah, turnaround time minus burst time will give me the waiting time. Now see, this is interesting. For process P4, the turnaround time was 6 and the burst time was also 6. That means this process P4 did not have to wait for the CPU at all. In fact, the CPU waited for P4 and as a result had a fall in its efficiency. But P4 did not have to wait for the CPU. So its waiting time is 0. And the last parameter that is commonly asked for is RT. RT is the response time. Response time is the first unit or the first instant at which a process gets hold of the CPU after it has arrived in the system. Now see, in order to find the response time, we need to make use of the NAT chart. Let's find the response time for P1. Now see, the arrival time of P1 is 1. And what is the first instant at which it got scheduled? 1th unit of time. So what is the difference? 1 minus 1 is 0. Look at P2. P2 arrived at time unit 1, but it first got hold of the CPU at time unit 4. The first time that it got hold of the CPU. See, P2 gets hold of the CPU here. In fact, P2 gets it only in this one slot. See, P1 gets hold of it here as well as here, but we are considering only the first slot at which P1 got hold of the CPU. So P2 gets hold of the CPU first at time unit 4 and its arrival time was 3. So 4 minus 3 is 1. Yeah, so P2 it's 4 and arrival time is 1, so 4 minus 1 is 3. 4 minus 1 is 3. Now, what about P3? See, P3's arrival time is 3 and the first time it got scheduled is 6, so 6 minus 3 is 3. And finally, what about P4? See, P4 arrived at time unit 16 and it got scheduled at time unit 16 as well. So 16 minus 16 is 0. So this is how you find the various times associated with a process using round robin scheduling algorithm for CPU contention. Now, oftentimes you're asked to find the average turnaround time, average waiting time, and the average response time. I think that is trivial from here. I'll just do one. I think the rest you can infer. See, if I have to find the average turnaround time, what would I do? In order to find the average turnaround time, I would simply take the sum of the turnaround times of each process and then divide it by the number of processes. So I have how many turnaround time? 9 plus 5 plus 8 plus 6. And how many processes do I have? I have 4 processes, so divided by 4. So this comes to be around 14, 22, 28 by 4. Okay, I'm lucky. 4 divides 28 without leaving a remainder, so this will be 7. So this is 7 units of time. Similarly, you can find the average waiting time and the average response time as well. Now, one thing to note here is, for preemptive scheduling algorithms, the waiting time and the response time will not be the same. But for non-preemptive scheduling algorithms, the waiting time and the response time are exactly the same. And another thing that we could be asked is, what about the efficiency? The efficiency of the CPU. So efficiency of the CPU. So how do we find the efficiency of the CPU? Look at the total execution time pattern. It starts from 0, ends at 22. So this is the total time for which the CPU executed on these processes. Now, what was the efficiency of the CPU during this time interval from 0 to 22? This is found by finding the useful time first. What was the useful time? The useful time is the total time that the CPU spent executing the processes. So you can see, instead of finding the useful time, what we could do is we could find the time for which, or the time slots for which the CPU was idle. So here we can find 1 time slot, and here we can find 5 time slots. So that's 1 plus 5, 6. So for 6 units of time, the CPU was idle. And what is the total unit it has been executing for? The total unit of time that the CPU has been executing for is 22. So 22 minus 6 will give me 16. So for 16 units of time, the CPU was functioning, was working. So it was active. And for the remaining time units, for the remaining 6 units, it was idle. So there lies the inefficiency of the CPU. And efficiency is generally expressed in percentage. So we'll multiply this by 100. And how much will you get? So I think you can do the math. So I'll just help you out. It's 800 by 11%, which comes to be around 7 are 77, 30, 22, 80, 11, 77. So I think it roughly comes to be around 72.72%. So the efficiency of the CPU is 72.72%. And one more thing that we can find from this is, what about the number of context switches? What is a context switch? A context switch refers to the change in the state of the CPU with respect to processes. See, here we find that the CPU is idle in this time slot, 0 to 1. The CPU is idle. Now at the next instant, the CPU has got hold of this process P1. So it has changed its context from the idle state to a working state, and working state with which process? With P1 process. So this is one context switch. Now look at this. P1 gets, P1 releases the CPU, or it is forcefully taken away from it. Whatever it may be the case, there is a change in the CPU's execution pattern from P1 to P2. So this is another context switch. And similarly, from P2 to P3, another context switch. P3 to P1, one more. P1 to P3. P3 to idle state back to P4, and then again P4 gets it. So this will be counted as a context switch because the process will be taken out and brought into the queue, and then again, since no other process was competing with P4 at this point, it will again be allocated. So there will be another context switch. So the number of context switches that we get are these lines, right? 1, 2, 3, 4, 5, 6, 7, 8. So we get a total of 8 context switches. We get a total of 8 context switches, right? And have I missed anything? Any parameter that we could have found? Yeah, what about throughput? What about the throughput? What about the throughput? Now see, the throughput is found by the number of processes that executed in this pattern, in this time interval, divided by this time interval. That means how many processes have executed in this time interval from 0 to 22? 4 processes. And what is the total time unit? 22 units. So the throughput will be 4 divided by 22. And throughput is also generally expressed in percentage, so into 100. So you will get roughly, I think, let's see, 200 by 11. So that comes to be around, 18.18%. Okay. So I hope this helps. Thank you.